Hello and welcome. This is a video for section 8.1 on finding the length along a function, something the math folks call arc length. A bigger idea I'm going to be trying to emphasize throughout chapter 8 is how to approach finding these values by slicing. Slicing is one of the big three main ideas in Calculus 2. And if you remember from the very beginning, we talked about area between curves, we were slicing, or volumes by revolution, we were slicing. We're going to continue on slicing and kind of culminating in section 8.4, where we're doing application problems. I'll mention this more in the 8.4 video, but if you're just trying to find formulas as opposed to learning the slicing technique, 8.4 might be very challenging because you're going to be searching for which formula to use for which kind of problem. But if we understand slicing, all the problems and applications in 8.4 are all basically the same. You just slice it up and add them all up together. Let me show you how that works with section 8.1 with finding the length along the function. And by the way, for those of you who are curious, the other two big ideas, the other two main ideas in Calculus 2 are integration techniques, such as integration by parts and substitution, things like that. And then the latter part of the semester, we're going to be doing what's called Taylor series, which is a way of decomposing a function. Like any complicated function, we're going to decompose it into an infinitely long polynomial, which sounds much more complicated than it really is. It's actually a very basic idea, but it's the most powerful idea because we can take any kind of weird signal or anything we're dealing with and just write it as a polynomial. May be very difficult to integrate strange functions, but it's very easy to integrate polynomials. All right, enough distractions. Let me get into the examples on length along a function, aka arc length. Okay, so let me just draw a little, random math thing. Mathematicians love drawing these like little random functions here. So let's say we start at point A and we end at point B. So what we're looking for in this particular section is how to find the length along the curve. So not along the x-axis. If you're going along the x-axis, you can break it up into little elements called dx, and all the dx's added together gives you the distance in the x direction. If you're going along the y-axis, then a little small change in the y-axis is called dy, and we add up all the y's, but we're not going along the x-axis, we're not going on the y-axis, we're going along the curve. We want to find, like, if you were traveling along this curve, what's the distance? So we need to break up the curve into small slices. So we're going to be doing that by drawing, like, for example, I'll just do it over here, a little slice right here. Okay, and we need a notation for that. It's not dx, it's not dy. You could call it df maybe, but the math people, they get to decide a lot of things. They call this ds. So ds is a small slice along the curve. That's just the standard notation we use for that. So if I kind of change where my dx and dy are located to make them just a little bit closer to the ds thing, dx would be something like here. Again, a very small change in the x direction, and dy be something like this. If I use a magnifying glass and kind of like look at this very closely, you'll see a curve. You'll have this section along of it called ds. ds. I gotta shake my pen. Give me 1 second. Okay, sorry. My pen is misbehaving. So we call this ds. And if we were going along the direction in the x direction along here would be called dx. And the y direction along here would be called dy. Whoops. dy and dx. And believe it or not, this makes a triangle. This makes a little triangle. I'll just push those up a little bit closer to the function thing. So there's a dx and a dy and a ds. And all we have to use is the Pythagorean theorem. We have a dx squared plus dy squared equals ds squared. You could divide all these things. You could just use algebra. You can divide everything by dx squared, dx squared, dx squared. The dx squared over the dx squared is going to equal 1. And then you have dy squared over dx squared, which I'll write as dy over dx squared. And then you have ds squared over dx squared, which I'll write as ds over dx squared. And then I square root both sides. And I get 1 plus dy over dx that's squared equals to ds over dx. And then I multiply both sides by dx to get rid of the dx, multiply by dx, multiply by dx. And when I get here, square root of 1 plus dy over dx squared. I'll move the dx on the other side just because it's habit. And over here, the dx is divide out, leaving just ds. That is a formula for ds. That's what we're going to be adding up. We need to be adding up all these little lengths along the curve. Each little length is called ds. So the idea is we took the function, we found what we're looking for, which is the distance along the curve. We took a small slice of that distance, we figured out a formula for it, and then we're just going to add them all up. And that's this formula here, by the way, that I have written on the lecture notes. ds is the square root of 1 plus dy dx squared times dx. You could actually divide by dy squared instead. And if you divide by dy squared instead, you end up with this alternative formula. And I'll show you how that's useful as well. They're both equivalent. They're just different algebraic manipulations of like the same formula, right? So there are different ways you can choose whichever one you want to use. All right, let's see this in action in an example. So the first example I have here is I want to find the length along the curve y equals sine x from x equals 0 to x equals pi. Now, although this is not necessary, I'll just give a visual aid for folks. The sine graph is the one that goes up and down, and it continues on. This top cycle here, or half cycle, goes from 0 to pi. And the top of the sine graph, the y values, never go higher than 1. Because that's the highest value on a unit circle. So that's our graph, and we're going to be trying to find the length along this curve, like the path here. We're going to be going along this curve, and these are all my little slices. And I'm going to add them all up to find out the total length or distance along the curve. So each one of these little things is called ds. So to find the length along the curve, I have the length of a slice. So the length of a slice is just ds. Right, that's the length along the curve. And so the total length would then be the integral of ds from a to b. So either from 0 to pi if we're thinking x's, or 0 to 1 if we're thinking y's. Let's do the x version so that it's sort of more standard for people to see. So this one up here, it has dx as its differential. That means this is the x version, right? So everything has to be in terms of the differential. Dx means everything has to be in terms of x. If we use the other version with a dy here, everything would have to be in terms of y's. All right, so we're going to write this as the integral. Back to red. This is going to equal the integral. ds is written as square root 1 plus dy dx squared dx. And as I mentioned, everything needs to be in terms of x. So the x values at the beginning is 0, and the x value at the end is pi. So that's our formula for the length. We do have to fill in what dy dx is. So we need to fill in this little guy right here. But we know what dy dx is. Dy dx is just the derivative. So if y is equal to sine x, then I know that the derivative is equal to cosine x. And so I can just fill that in to my formula. So that means my length is the integral from 0 to pi, square root of 1 plus the derivative cosine x squared, which we oftentimes write like that, and dx. And if we can calculate that antiderivative, plug in the 0 and the pi and subtract, we get our length. So that's how arc length works, right? We just break it in little pieces, and we fill in the formula, and we add them all up. So to do 1 plus cosine x squared square rooted, there are different ways of doing it. you have to kind of use a substitution, and you're going to have to sort of use a trigonometric substitution. For these kinds of problems, I'm okay with using technology unless the problem specifies otherwise. So I'm not going to spend time on this lecture going through all the steps on how to anti-differentiate this thing. It's just not our goal right now. Our goal is to just try to understand slicing, and in this case, how to find the length along a curve. So I'm going to go to some math engine. I'm going to go to Wolfram Alpha. It's usually my go-to, and I'm going to integrate from 0 to pi of this function. So here's Wolfram Alpha. I'll just say integral from 0 to pi of, I think we had a square root of 1 plus cosine squared of x, something like that. Let's see if it does it. It's going to put into like nice form what I typed in. So integral from 0 to pi of 1 plus cosine squared x dx. We can double check that that's the correct formula or correct integral, but it is. I remember 0 to pi 1 plus cosine squared x dx. So I typed it in close enough for Wolfram Alpha to recognize that's what I want, and it gives an approximation of 3.820. So 3.820. So that's the distance along the graph. From 0 to pi, by the way, is 3.14 because I started at 0 and it ended up at pi. So it's approximately 3.4 in the x direction. We know it's approximately 1 in the y direction, or maybe it's exactly 1 in the y direction. And along the curve, it's longer than either of those, which hopefully kind of makes sense because you're not going straight, you're going in a curve. It's about 3.82 whatever meters or whatever you're measuring the axes in. So there's an example of how to find the length along the curve. I'll do a couple more examples, or maybe I'll do one, ask you guys to try one. So for my example B here, I'm going to find the length along the arc of a curve. Now this one I gave as x equals from 0 to 1. Now it doesn't really matter if we know what this looks like. You can go to Desmos if you like, or even Wolfram Alpha and try to graph this thing. It doesn't really matter what it looks like. It's going to be something. I'm going to be dividing up in little segments, little ds segments, right? So we're just going to add up all the little ds's. So the length is going to equal to the integral of ds. We got to find out where it starts and where it ends. So apparently it starts at y equals 0. So maybe let's just put this down here. So it starts at y equals 0 and it ends at y equals 1. So these are y values where it starts and ends, which kind of leads me to believe they're giving me the function in terms of y. They're giving me y values. Maybe they want me to put everything in terms of y, right? Maybe that would be something that they're intending to do. Now, mind you, you can do whatever you want. You can put these in terms of x's if you want. We can find out what x is. If y equals 0, I get 0 squared plus e to the 0. So y equals 0 corresponds to x equaling 0 plus 1 or 1. So this is a x value of 1 here. And if I put in y equals 1, I get the x value of 1 squared plus e to the 1. So it ends here at 1 plus e. So you're welcome to try to put it in terms of x's. You're just going to have to compute a bunch of stuff. You're going to compute the starting and ending x values like that. So just for fun, I'll put it in terms of x's, since that we just did. If you want to look on the previous page for the formula for ds, or you might remember it by now, it's square root of 1 plus dy dx squared times dx. We need to find out dy dx. So our function here is x equals y squared plus e to the y. Okay, well, it's not so easy necessarily to find dy dx. Let's put it this way. It's not easy to solve for y in this equation because y is squared and exponentiated and stuff like that. We could find dx dy. That would just be differentiating both sides with respect to y. Let me just make that obvious. I'll differentiate this side with respect to y and differentiate this side with respect to y, right? Just that's my dependent or independent variable down there, dy. So I get dx dy. The derivative of x with respect to y is called dx dy. The derivative of y squared with respect to y is called 2y. And the derivative of e to the y with respect to y is just e to the y. So that's what dx dy is. To find dy dx, we can just sort of reciprocate. We could just flip this. So dy dx would equal 1 over 2y plus e to the y. I feel that algebraic step isn't emphasized enough in algebra. Like people are always used to like multiplying and subtracting, but you could just literally flip both sides. That's doing the same thing to both sides. And that solves for dy dx. So I could put that thing in for there, right? And what I get is I would get length equals integral 1 plus this big fraction thing, 2y plus e to the y, all squared dx. Now remember, the differential is the key. The differential here is dx, which means everything has to be in terms of x. Our limits have to be in terms of x, which is x equals 1 to x equals 1 plus e. And the integrand needs to be in terms of x. So we need to put these in terms of x. Well, what is 2y plus e to the y in terms of x? I don't really know. I know that y squared plus e to the y is exactly equal to x. I'm not sure how to solve for what y is and how to find out how to put 2y plus e to the y in terms of x. But because my differential is dx, everything's got to be in terms of x's, which means we can't do this problem until we turn this 2y plus e to the y into some version of x's. The only reason I went down this rabbit hole is to show you that although you can do it in terms of x's, it may not be the easiest way. It may be much easier to do it in terms of y's. In fact, in this problem, it is much, much easier to do it in terms of y's. So let me flip back to the last page and remind you what the formula is for ds in terms of y's. So up here, I had the formulas. The one in red was the one using dx as the differential. It's 1 plus dx, dy dx squared times dx. The alternate version in terms of y is almost the same. It's instead of 1 plus dy dx, it's 1 plus dx dy squared, and it's got the dy there. So it's virtually the same thing, except we're doing the derivative dx dy, and it's in terms of y's with the dy. All right, so for this one, I'll do green over here. We're going to integral the formula, if you want to flip back there, if you remember it, is dx dy squared dy. Now, of course, I do want to emphasize again, because we have the differential dy, everything's got to be in terms of y's. So our length along the curve has got to be from y equals something to y equals something. The smallest y value is 0. Largest y value is 1. I get square root of 1 plus dx dy. By the way, we found dx dy. It's right here, right? That was how we just differentiated both sides to find dx dy. So we don't have to do any kind of reciprocation or to solve for anything. It is literally just 2y plus e to the y. Now remember, the formula says dx dy squared, so I got to square this thing. And then it's times dy. Now everything is in terms of y already, right? Our differential is dy. All the stuff here is in terms of y's. The limits are in terms of y's. Everything in terms of y's, so we're good to go. We can try to do this by hand, or as I'm going to do right now, we're going to use technology to calculate this thing. So we get 2y plus e to the y is the derivative. Or I'll do it a different way. Integral of square root of 1 plus, and we got 2y plus e to the y squared and then dy from y equals 0 to y equals 1. Let's see if it did that. It'll try to put it in a way that you can see it. Square root 1 plus, they put the e to the y first, e to the y plus 2y squared dy. I'm almost positive that's what I wrote on my paper. I'll just double check real quick. 1 plus 2y plus e to the y squared dy from 0 to 1. That does look like what I typed in. Yeah. So it computed the total length as 2.924. All right, so there's a couple of examples of arc length, one using sort of the dx version of the formula and one using the dy version of the formula. I have one last problem here as an example. It's not terribly different than anything else once you understand how to slice things up, just a bunch of DS's that you have to compute. They're pretty much all the same kind of problem. So for this one, part C, I'm going to invite you to try it, without watching me do it first. You don't have to if you don't want to, but it's a great opportunity to see if you got all the steps down. And for this one, I'm going to ask you to also practice doing the antiderivative without using technology. So I did use technology for parts A and B, but for this example, part C, if you want to give it a go, which I really hope you do, also see if you can remember your integration techniques and actually do the antiderivative. It's not as complicated as the antiderivatives in A and B. So hopefully maybe you can get an idea of how that works. And then I'm going to just wait for a couple seconds and hopefully people will pause the video and then come back now. Okay, so welcome back if you to do that. And I'm going to go ahead and see if I can find the arc length without using technology. So once again, you can do a visual aid. It doesn't really matter if you know what x to the 3/2 looks like. It's some function thing. We're going from x equals 1 to x equals 4. Right, that's the notation, 1 to 4. And it's when they do that bracket thing, it means including 1, including 4. And if they don't specify, it's always for the input variable, for the independent variable, which is x. So 1 to 4 means x equals 1 to x equals 4. You may see that in the homework. So just kind of remember that's the notation the math people use. We're going to break these up into little pieces. Each piece is called ds. And so our length is once again going to be an integral ds. I'm going to try to put it in terms of x's this time. So I'm going to do 1 plus the derivative dy dx squared rooted times dx. And I have to compute dy dx. So this is my y function over here. And its derivative dy dx is equal to 3/2 x to the 1/2. All right, so put that into my formula. I'm going to get integral square root of 1 plus this thing, 3/2 x to the 1/2 squared dx. So because it's a dx, everything has to be in terms of x's. I know what the limits are in terms of x's already. It gives me x is 1 and x equals 4 as the two endpoints of my interval. And then I have to compute this derivative, and we're going to do it by hand. So first of all, I don't recognize this, so I'm going to simplify it using algebra. I'm just going to use some basic algebra first before I attempt to use any fancy algebra techniques from calculus. So I can square this thing, right? And the square of 3/2, 3/2 times 3/2 is 9/4. And the square of x to the 1/2, x to the 1/2 squared, well, those are inverses, so it's just x dx. All right, so I used algebraic simplification to get my formula here. And this, again, is not something which is a recognizable formula from our antiderivatives formula sheet, but I can simplify this using a u substitution. So I'm going to use a u substitution equaling the complicated part inside, 1 plus 9/4 x. I'm going to have to solve for dx to convert everything in terms of u's. So du dx is equal to, well, derivative of 1 is 0. Derivative of 9/4 x is just 9/4. So that means dx is equal to, let's see, if I flip those things or if I move those over, I get 4/9 times du. So I'm going to put this version of dx into there, and I'm going to put this version of u into there and see what I get. So these are x values, by the way. These are not u values. So x equals 1, x equals 4. I can put the square root of 1 plus, well, actually, the whole thing, 1 plus 9x, not just the 9 fourths x, but the whole thing, 1 plus 9 fourths x. That whole thing is equal to u. So I just have u here, right? And then I have a dx, but dx I need to substitute is 4/9 du. Now I'm going to show some people like just converting everything in terms of u's. Like we can just convert these into u's. So if x equals 1, what is u? Well, remember, u is equal to 1 plus 9 fourths x. So if x is equal to 1, that means u is equal to 1 plus 9 fourths, which is 13 fourths. And if x is equal to 4, the other limit, then u is equal to 1 plus 9 fourths times 4 is just 9, so it's going to be 10. So if I were to convert these into u's, I would write L equals integral. The bottom one is 13 fourths, and the top one is 10. And that would be the square root of u du. Let me take the 4/9 out in front, so I don't have to worry about a constant either. So all I have to do is I have to differentiate u to the 1/2, and then plug in some numbers, and I will find out my integral, which is my length. Okay, so by the way, you don't have to convert everything in terms of u's. What you can do instead is you could just substitute back in terms of x's. So once I do the anti-differentiation, this would be 4/9. The antiderivative of u to the 1/2, u squared of u is u to the 1/2. The antiderivative of u to the 1/2 is going to be u to the 3/2 times 2/3. And that will be integrated from u equals, or evaluated from u equals 13 fourths up to u equals 10. If you didn't want to put it in terms of u's, if you want to just leave it in terms of x's, you would just put this back in terms of x's by substituting back at the end. You could just make that back in terms of x's. And then you would be going from our traditional x equals 1 to x equals 4. You can either convert everything to u's or just convert everything back to x's. It's really up to you. I just figured I'd show an example of converting it to u's because that's popular for some people to do that. Just convert it to the new variable. All right, so let me write this 13/4. I'm going to write it as a decimal just to make things easier. Let's see, that's 3.25. I'm tired of writing fractions. Okay, so what do we get here? We get 8/27. We get u to the 3/2. Let's see if this works. Nope. Alt maybe. Trying to pause it. There's supposed to be a pause, like. Okay, so I got my pen working again. So we get 8/27, we get u to the 3/2, and we're just going to plug in values of 13 fourths, no, 6.25 and 10. Okay, so that's going to be 8/27 times 10 to the 3/2 minus 6.25 to the 3/2. And I could use a calculator to get a decimal approximation because the directions do not say I can't use technology at all. It just says don't use technology for the derivatives or integrals. So I can get this and I can write a decimal approximation. You don't have to if you don't want to. Whoops, forgot one more parentheses. You can leave it like that if you have the right number of parentheses, or you can get a decimal approximation if you prefer that as well. So, but this is fine, leaving it like this. That is the length that we could get a numerical value for if you wish. All right, well, hopefully you gave that a try, and hopefully my showing of the solution process was helpful. And hopefully this lecture on 8.1 helped you understand how to find the length along the curve, as well as more of the idea of slicing. Please reach out if you have any questions or want any more examples or have any what if scenarios, and I'd be glad to help you with some more of these problems. I hope you have an enjoyable day and maybe see you in the next video.